When most of us think of landslides, we think fast and we think destructive, like the big landslides that commonly wipe out sections of Highway 1 along California's Big Sur region. However, there's another type of landslide you may not have heard of before called an earth flow, which is a slow-moving landslide that creeps along at rates of a few centimeters to several meters per year. This is the type of landslide that I study.
So I'm actually standing on one of these slow-moving landslides right now, and while it might not look like much, these landslides actually exist all over California, and they have a huge range of effects, from things like progressive infrastructure damage, to ecology, creating habitat for endangered species, to huge effects on sediment supply and landscape evolution over geologic time. So there's something that in earth sciences we care a lot about figuring out how and why they work. To start to understand what leads to fast versus slow landslides, the UCSC Geomorphology Group has spent the last 5 years studying conditions at this site, known as Oak Ridge Earth Flow. And through a combination of geophysical techniques to image the subsurface beneath where I'm standing, and pore pressure sensors that can monitor the water conditions underground, we've discovered that this site maintains an elevated water table relative to the hills around it. And that's really important because we know that whether a landslide will fail or not is determined by what the height of the water table above the failure plane is. So this elevated water table means that this landslide is constantly near failure, which explains why it moves consistently throughout the wet seasons here in California rather than failing once like faster landslides that we may be familiar with.
But there's a second part of the story that relies on the local geology. This is an example of the kind of rock that makes up Oak Ridge earth flow. Very deformed and very clay-rich. Water has a hard time moving through it quickly. If we were to stick our head into the ground at Oak Ridge, we would see a very thin layer of soil, followed by a couple meters of this material, broken up into fractures by chemical and physical weathering processes. This is the variably saturated zone, the subsurface region that is sometimes saturated, sometimes not, depending on the position of the water table throughout the year. Beneath that lies fresh, unweathered rock that stays saturated year-round. In contrast, many faster landslides occur in a material like this sandstone. A rock like this weathers differently than the clay material that we deal with, creating a much thicker zone in which the water table fluctuates over the year. This has implications for the amount of stress that each site can build up above the landslide failure plane, and as a result, the type of failure that will occur. Here we're looking at two example hill slopes made up of different types of bedrock. The one on the left has a thick weathered zone beneath the surface that allows for a lot of water table rise, and the one on the right is more like our landslide, where the water table is always close to the surface and there's not much room to grow. In the first case, as the water table rises due to winter rains, we can get 10 or more additional meters of water, which causes a lot of stress to build up on a potential landslide failure plane. In contrast, at a site like Oak Ridge, the water table only has 3 meters or less that it can rise before it reaches the ground surface and spills out as springs. So in a big storm, the first site might see a large water table rise that causes it to blast through any resisting forces and fail catastrophically. But a site like Oak Ridge, even if it gets the same amount of rainfall, and even though it already started closer to failure, can only fail slowly and in small increments because it is a built-in release valve that prevents the pressures from ever getting too high. Ultimately, these landslides are a product of the rocks on which they are born. They fail slowly and incrementally over many seasons because continually elevated water tables drive them to the brink of failure. Yet there's never enough room to build up catastrophic pressures before excess water spills out as surface springs, relegating earth flows instead to a life of slow creep.